And with that, I'd like to welcome Dennis Dalessandro, Cornelis Networks, presenting his session on Cornelis Networks CN5000 adapter and software update. Dennis is a kernel engineer and software engineering manager leading in the development of Omnipath architecture drivers.
Alrighty, so this here. All right, you guys see my screen?
We see your camera, but not your screen. There we are.
How about now?
There it is.
Alrighty. Okay, so, thanks, Phil. So I'm Dennis from Cornelis Networks. I'm going to talk to you guys a little bit today about our CN5000 technology and specifically talking about our software. If we could advance this slide, there we go. All right, I'm sure everybody read that. So last year I gave a talk, and the focus on that was how we get our code upstream and how we maintain being a upstream first development organization. So I just kind of want to reiterate that with this picture of mine, because this is going to come into play later. We develop the code, it goes out to kernel.org, the distros pick it up, and then it ends up on our GitHub, and we add certain things on top of that. Those certain things mainly being GPU support, and then can go to customers from there. So let's just keep that in mind. So like I said, I want to talk this year about how we keep doing this upstream first while we're developing new hardware. We're still figuring that out, and so I'm going to let you guys know kind of what we're doing and talk a little bit about what is CN5000, and some of the challenges that we have as far as from the software point of view. It's not a sales pitch. Obviously I want you guys to run out and buy the stuff when it's available, but we've got people that'll handle that. My goal is to get our software upstream when the hardware is available, and so this is kind of a precursor for that. So with that, go over a little bit about what is CN5000. It's the name that we give into our next generation fabric. It's consists of adapters, we have switches, software, and then we qualify cables. The part that I'm involved with is the driver, so I'm mainly going to focus on the adapter and the software, because that's what I know. But I will show you guys at least what the switches look like. So we have two switches. We have an edge switch, which is a 48 port switch. Each port's 400 gigabits. It's air or liquid cooled, or some kind of hybrid. The director switch is a 576 port, 400 gigabit per port switch. Again, air and liquid cooling for that guy. And there's a URL there that you can go to if you want to get more information. I just pulled these images off the specs off of our website. The stuff that I really work with is the HFI, our adapter, which HFI is the host fabric interface. And this one is going to be a PCIe Gen 5. It's a low profile card. It does air or what we call indirect liquid cooling. It's got some sort of this heat pipe that connects from the ASIC to a cold plate on the server. It is available, or will be available, 1 or 2 fabric ports, each one at 400 gigabits, as opposed to the 100 gigabit, which is the aptly named OFA 100. From a technical detail point of view, OFA 100, that was known as Wolf River. That name leaked out of Intel a long time ago. There's nothing secret about that. CN5000, the ASIC on there, that chip is going to be called Jackal River. Basically, I don't think code names really matter, so we're using it in the code, so you're going to see it anyway. So there, it's Jackal River. We still take advantage of 16 DMA engines. This is for our SDMA way of sending data. This is where the card pulls data in. User space has to work with the kernel to set up the descriptors and then pull that in, because this is the DMA engines are shared between user space and kernel space. This is generally for your larger data transfers. The OS bypass, and for smaller stuff is our PIO. We have 160 send contexts in Wolf River. We have increased that to 240 send contexts for Jackal River. The amount of memory for PIO has quadrupled from 1 to 4 megabytes. And the same thing goes for receive. There are 160 receive contexts in Wolf River, 240 receive contexts in Jackal River. If anybody has looked at our code closely, we have support for what's called 16B packets. This is named because there's 16 bytes in the header. A traditional InfiniBand packet is 9 bytes. Wolf River operated on 9 bytes in hardware. We supported 16B and 10B and 8B packets, and they were in this what's called bypass mode, which meant the hardware didn't do anything with them really. So it was all done in software. With Jackal River, this is a fully supported native packet type, so it's all done in hardware now. And this why the 16B stuff is really cool is because it enables fancy stuff like adaptive routing. We can use a much larger lid space. We got 24 bits versus 16 bits. And if anybody remembers, I talked a couple years ago at an OFA conference about SE Linux and how we were supporting SE Linux. One of our limitations at the time was we only were able to support 16 P keys in hardware. We've increased our P key table from 16 to 1024 in Jackal River. So we're able to do the full MLS stuff. So why am I telling you guys this stuff? Should this stuff be secret because the hardware's not out there yet or anything? But honestly, no. Everything that I'm talking about here is literally in the code. It's stuff that you'll be able to see from the code. And the motivation for why I'm doing this is hopefully that it makes getting our code accepted upstream easier. It lets the open source community know more about what we're doing and is able to contribute more when people understand what our hardware is actually doing. There's also a number of settings and tweaks that'll be in our tuning guide, and this kind of stuff and information will hopefully helps explain some of that stuff. And it's just really cool stuff. But if you're bored now, just wait, because we've got code to talk about in a minute. Back to what I was talking about, the technical stuff. So receive descriptors, they have increased from 64K in Wolf River to 128K in Jackal River. We do support 8 VL still, plus VL15 for management. And one of the big changes that we have here in Jackal River is going to be PCIe SROV support. And we have a lot of code changes that are coming for this. The HFI driver was just not designed to support SROV before, but it will be now. As far as hardware support, we have the basic SROV, isolation support, but there's also, we have these dual loopback ports. So system images are able to actually talk to each other over a fast interconnect. We also have this thing known as a C port, which is a processor that's embedded on the board. This is handling all of the fabric management and link management stuff. Things that we used to have to do in the driver, we now can offload to the C port. So our code has 10,000 lines of stuff in it to process MAD packets. We don't have to have that anymore. That's all done by this extra micro. Our receive side matching, we are able to do a deeper packet inspection. This is what helps us land packets for, for IP over IP for our advanced AIP, advanced IP. So we use an RSM rule for that. We are certain RSM rules to land packets on context for user space, et cetera. So we went from only having 4 of those rules to 32. I'm not going to go into what we could possibly do with them, but you can imagine these could be very useful for different things. And that's kind of, I'd like to hear from people too. If this sounds like something that you can use, then what would you do with them? Right now, there's no interface that exports this stuff to users. It doesn't mean that there couldn't be. And then there's lots of other bells and whistles in the hardware, but those are the main things. So as far as the upstream plan goes, is this going to be the HFI2? And I thought about that, and I had a conversation with the maintainer maybe the last time OFA was actually in person, and his response was, please God, no, don't make an HFI2. So I tend to agree with that, and because Jackal River still has a lot of the same concepts as Wolf River, it's just bigger, faster, stronger, better. We can stick with the same driver. So do we really need to keep calling it HFI1 instead of just having an HFI driver? Probably not, but nobody wants to change it. I mean, nobody's changed the name of the subsystem from InfiniBand to just RDMA. Names tend to just kind of linger, even though there's like 50 RDMA drivers and one InfiniBand driver these days. Anyway, our plan though is to delete QIB as well. So that was previous to Wolf River, previous to OPA, which is an InfiniBand driver. I've done up a pack series to remove QIB multiple times over the past few years, and every time I do, without fail, I end up finding somebody else that has a problem or is actually using this on some old cluster somewhere. But I'm kind of planting the flag in the ground now that QIB is on its way out. So it's been end of life for a long time. It's just supported as an upstream project. So we're going to be deleting QIB as part of the Jackal River upstream, which that's a lot of code and should actually make kernel people happy, because we should end up having a net loss of lines of code by removing that entire driver. So that'll be good. RDMA VT, this is another thing I talked about at an OFA conference years ago when we first did Wolf River. This is our software verbs implementation. When we released the HFI driver in Wolf River, it was basically a copy of QIB driver, but made to work for OmniPath. Obviously, there were problems with that. The kernel community was not happy. So what we did was we took all of the common verb software implementation stuff and put that off into its own kernel module, which was already VT. So with QIB gone and HFI1 able to support both the drivers, do we still need RDMA VT? And the answer to that is no. However, at this time, I don't have any plans to actually remove it and shoehorn all that stuff back into the HFI1 driver. It's generally invisible to users. People don't have to know about it. It's more of a pain for packaging and just another driver to have to worry about for automation and stuff like that. So, someday we run out of things to do, maybe. All right, so I'm going to go over some of the big changes that we've had to make in order to get this software going here. So I keep saying Wolf River and Jackal River are similar, and they are similar in terms of, they both have SDMA and PIO, and they operate sort of the same way. But when it comes down to it, there's a lot that's changed. So if we make a field bigger or move something, that sets off a chain reaction of lots of different registers moving offsets, and we have to deal with that. So there are a lot of patches that I'm still trying to deal with that are where we parameterize accessing a register because it's got two different addresses, one in Wolf River, one in Jack River, but it's used sort of the same place. So we've got a lot of those patches that parameterize that, and then, you know, a patch that actually uses it. With QIB, what we did was, or what they did, because QIB was way before my time, was for each chip there was a set of function pointers, and those functions for each of the different chips did 98% of the same stuff, and then they had one little thing that was different. So instead of having all those different copies of the code, we're going to handle all those specific little things, you know, individually. And that's what's there's going to be a lot of code, a lot of patches just for that. Whether I'm going to squash these down or submit them as is, I'm still not 100% sure. It's, you know, either bigger patches or lots of patches. There's going to be a lot, no matter how we deal with it. Oops, not too far. Okay, so if you remember back, I said Wolf River had one port, Jack River has two ports in general. We tried our best when we were doing Wolf River because we wanted it to be extendable to operate on multiple ports. So we had this thing called a PPD, which was our per port data. It's an array of ports. Over time, we didn't always stick to that, and people started using, you know, just the first entry in the array, the only entry in the array, and just blindly using that, which is not, you know, super technically difficult to get around, but there's a ton of it, and there's a lot of code churn associated with this. And, you know, 7 years this code has been out there, and so it's continually been moved around and modified and changed. And so finding all these spots with, you know, where we have to propagate a port through versus just guessing or knowing what the port is, that's been quite a feat. So like I said, HFI1 has, you know, this PPD, this per port data, which lives in a device data structure. So one of the exercises that we've done is we've taken the stuff that's, you know, really differs per port out of the DD, and putting it in the PPD. So these are data structures that pretty much are available anywhere you are in our driver. So for Seaport, there is for as much as it buys us, we also have to create a protocol for us to talk to Seaport. So when the link status changes or a lid changes, we have to know about it. So we have to put in this, you know, a protocol to be able to talk to Seaport, which is, you know, through a register interface. We actually also have the ability to talk over loopback ports. So, and that'll be a much higher speed way of talking to Seaport. Not sure if that's going to be there when we first drop the driver or not, but it's definitely something we're working on. The big thing is that with Seaport managing all this stuff, the driver doesn't have to do it. Like I said, the MAD packets processing takes up a lot of code, and there's continually stuff going on in the fabric, telemetry, and, you know, performance management or performance monitoring packets, and just all these things are flying by in the fabric, and the driver has to, or in Wolf River, you know, it had to process all that stuff. And if it's processing that stuff, it can't be doing what it's supposed to be doing, which is sending user data. So by, you know, dealing with this in Seaport, it's going to, you know, make a big difference on how fast we're able to get around to processing packets, which is, it's a goal. As far as the user API changes goes, technically there's no reason that we have to change the user API, other than to know what port it is. Looking ahead, we actually don't have a port number in there currently, so we have to do that. But when we first upstreamed Wolf River a long time ago, there was a big backlash about the character device that we have, and we agreed that we would remove it eventually. Well, eventually is here. There's a lot of heavy resistance to us changing our API until we get rid of that CDEV. This is something that I don't necessarily see eye to eye, but I've been overruled time and time again by the kernel community about this. So we are going to acquiesce to their demand, and it will go away. The plan right now is looking like we're going to use the uverbs FD as our command and control path. So opening contexts, setting up TID receives, things like that, sending SDMA requests. That will go through, actually, no, not sending SDMA requests. Sorry. All of the setting up of things will go through the FD. We still need to have our own FD for the data path. So for the high speed data of sending the work requests into the driver is going to be ideally with our own character device file descriptor. The difference is that this will be owned and created by the IB core and not owned by the driver, which is managing of the life cycle is one of the main complaints of why we can't do that. One of the other things that we want to do is IOU ring. So, and there, it turns out there are some complications and issues around IOU ring. I have some concerns with IOU ring, and I don't know that we want to impose that on the verbs FD. One of the benefits, though, of doing this is the memory registration for DMA buffs and GPUs. Sorry. So anyway, all this code is still a work in progress, but we should have an RFC out soon for it, which will talk about all this stuff in way more detail. So, the 800-pound gorilla in the room is GPU. I mean, yesterday, I think every talk talked about GPUs, and, with AI, GPU is very, very important. And this applies to our OPA 100 stuff as well. And everybody knows the problem with GPU code is it's not upstream. So I'm not going to get too high on my soapbox here and jump up and down about it, but it is an issue that we as an upstream first development organization have to deal with. So we just, I say we have to hold our nose and just deal with it. This is where we leverage the distro kernels and their drivers, which are built with our upstream code, and we glue on the GPU support and make that available on GitHub. So that picture that I showed earlier, and I'll show it here again in more detail. But before that, I just want to mention that there's no good way in the kernel right now to hook into non-upstreamable code like that, and there's reasons for that. Linux's approach is, we penalize users and we force them to complain to the vendors and try to get the vendors to switch that way. It hasn't happened. It's not going to happen. And yes, there are plenty of technical issues or why and how, but the point I make is kernel people are pretty smart. If we wanted to as a community, we could come together and come up with some way of addressing this problem, rather than being obstinate and say, too bad. And yes, it's a slippery slope. If you start doing this for GPU, where does it stop? But I think, GPU and AI is such an important thing right now that Linux is doing itself a disservice by making it harder for that stuff to be integrated with it. So, all right, soapbox off. So just to reiterate, this is, the picture of how our stuff gets there. And the bulk of our changes that's going on to our GitHub is GPU code. There is some diagnostic stuff as well, that is not upstream, and it was submitted upstream, but upstream didn't like it, so it didn't make it into the kernel. It's nothing that people have to run. It's just sort of, nice to have stuff. GPU, that's different. That is what people do want. And customers, they're going to run the distro drivers as is. So, but they want to be able to run with GPU. So we have to glue it on top. And that's just the world that we are in right now. So how do we deal with this? So if we can't upstream our GPU code, one of the ways is to limit how much GPU code there is. So our previous support for GPU had GPU code sprinkled in all over the driver, and that driver was one driver for every distro. So there were all kinds of if def rel 6.7 or SLES 15.3, whatever. There were all kinds of stuff like that in there, which is an unmaintainable mess. So we, about last year when I presented that whole picture that we were talking about, we threw that away, and we literally take the distro code that the customer's already running and just add what we need. So we had to take all of that GPU stuff that was spread out throughout the driver and kind of modularize it. And it turns out that the bulk of it is related to page pinning. So now what we end up with was we have a system memory pinning module. It's not really a module, but for thinking about in the abstract, I'm just calling it a module. And then we have one for NVIDIA, and we have one for AMD. The NVIDIA and the AMD clearly don't go upstream. Those get added in as part of the stuff that we add to GitHub. So it makes it easy to drop this stuff in without a whole lot of engineering. Now, that does mean we have to pay attention to when system memory pinning changes happen upstream. If we're not making them, then we have to make sure that we evaluate and port that into the GPU paths if needed. So, DMA buff, I think we heard about this as well. This is definitely a step in the right direction where we want to go. There's one main GPU that supports it now, and maybe another one coming soon, hopefully. So this is why we want to use the verbs device. So the verbs memory registration already supports DMA buff. So rather than having to duplicate all of the code to pin those pages, we just want to be able to use what's there. DMA buff for us internally as a driver is just another drop-in module type thing, just like NVIDIA and AMD. The difference is it will be able to be upstream just like the system memory hitting. So high level status for all of our stuff here, the FM, which is an insanely complicated piece of software. It does some amazing stuff. This guy is fully in distro, and it will support Seed 5000 right out of the box. So kudos to those guys. libpsm2, it's still here. It's going to be active as long as OPA 100 is around, because that's still the main supported vehicle there. But the real plan for CN 5000 is OFI libfabric, which is our OPX is our native provider for libfabric. The fast fabric tool. So if you ever type OPA tab on a Linux distribution, you get like 90 OPA commands. That's more than we need. So, we're in the middle of revamping that kind of stuff. Pruning the tree of some of the things that we, don't really need, and looking at using more community accepted tools like RDMA tools. So more details on this will be coming, but if you've got, as an end user, ideas or things that you just drive you crazy, reach out and let us know. Let me know, and I'll make sure that feedback makes it to, people that are looking at this. Obviously, kernel stuff I keep talking about is coming soon. It's just not there yet. So CN5000, the hardware is coming later this year. In the meantime, we do still have OPA 100. It is still fully supported. There are lots of people using it. It is actively being developed. We've recently added AMD GPU support. And I had talked about how we had the GPU codes scattered throughout the driver, and we moved it on to this new way of doing it that broke PSM, but we have made a compatibility shim for PSM2 CUDA support. So that's there now too. And that is it.
Great. Thanks, Dennis. We have two questions that I've been asked. One is, you mentioned a few Linux distributions. What Linux distributions do you support?
We mainly support RHEL and SLES. We try to support the current and one back. We are looking at supporting other distros as well. Ubuntu is a popular one. Ideally for those, the primary vehicle would be just running the distro. And the idea is that you shouldn't have to download extra stuff, and GPU being the exception, but you should just be able to take the distro and just run it on pretty much anything.
Cool. Thank you. And the other one I have received is, are there any thoughts or plans about an Ethernet engine on the NIC HFI? There are a lot of interest in the UEC these days.
So Cornelis is, can't say too much about it, but Cornelis is part, we did join the UEC. So it is something that we are definitely looking at, and there will probably be, more customer facing stuff coming out before too long about that. But I don't know of any specific plans or anything like that I can get into.
Cool. Okay. Are there any other questions, Dennis? I do not see any hands raised. So thank you very much. Thank you. Another good talk. I really enjoy your talks.